No, so that's the audio. No, that's fine. Okay, so let's get started. So the last session for today is a panel discussion, about scaling. So scaling has a huge impact on deep learning. So what is the role of scaling when we move away from the typical train test paradigm? Like, for example, in frameworks like lifelong learning or meta learning, right? Like, so, and what is the role of academia in the race for scale? So that's the topic that we are going to discuss, and like we have like a very interesting set of panelists who are going to answer some of the questions that you have asked in the Slack. So like from the right, like so we have Irina Rish. So Irina Rish is an associate professor in the computer science and operations research department at the University of Montreal and a core member of MILA, the Quebec AA Institute. She holds the Canada C4AA chair and the Canadian Excellence Research Chair in Autonomous AA. She holds MSc and PhD in AA from University of California, Irvine, and MSc in Applied Mathematics from Moscow Gubkin Institute. Her research focuses on machine learning, neural data analysis, and neuro-inspired AI. So then we have Kevin Murphy. So Kevin Murphy is a research scientist at Google in Mountain View, California, where he works on AI, machine learning, computer vision, and NLP. Before joining Google in 2011, he was an associate professor of computer science and statistics at the University of British Columbia in Vancouver, Canada. He has published several papers as well as I think this bio says a 1100-page textbook called Machine Learning: A Probabilistic Perspective, but I think it has expanded now into two separate books. And he was awarded the 2013 D Group Prize for Best Book in the field of statistical science for his previous edition of the machine learning book. Okay, so then we have Tinne Tuytelaars, like whom like we have already introduced yesterday, and we have Doina Precup, who is our general chair, and this panel is going to be moderated by Razvan, who is the program co-chair of CoLLAs. So
Thank you so far. Okay. Thank you so much. So hopefully this works. Okay. Okay. So I'm gonna start the panel. So I have like a warm up question that is not about scaling. And the question is more around CoLLAs as a conference is focusing on these paradigms that might help us move away from the stationary assumption. I basically want to see whether the panelists have thoughts on that. Is this something important? That is this the right time to look at this kind of questions? How important do you think it is to move away from the stationary assumption? Like what are, yeah, from your perspective, what is the problem with IID assumption? And I'm not sure if anyone wants to start.
And it's a crucial problem, which is why I'm I guess general chairing this conference and supporting this. There's the IID assumption. There's other similar assumptions like the Markovian assumption in reinforcement learning, or the stationarity assumption that you have policies that will have stationary distributions. And we know that these assumptions don't hold in practice. And if we want to deploy machine learning systems, reinforcement learning systems in large scale setups, we need to move away from that. And I think, as Rich Karana pointed out this morning, actually, there has been a lot of work over the years that tries to move away from these assumptions. I think it's just, from my point of view, it's more like bringing together people who are caring about these things in different kinds of machine learning problems and having them talk to each other. But really, a lot of people have been thinking about this over a long time.
I agree.
Yeah, no, I think IID, going beyond the IID assumption is critical, right? I view distribution shift and adversarial attacks and online learning as all related. I mean, I think whether we need this workshop or not, I don't know. I think this should just become part of mainstream ML because supervised learning is basically solved. I'd push back a bit on Richard Caruana's thing. I loved his talk, but I wouldn't characterize that as at all to do with IID, sort of non-IID. It's just a vector-to-vector mapping, right? It's like pixel-to-pixel mapping, like UNets or whatever, and it's fully supervised with no assumptions about distribution shift. So he was asked about what happens if you extrapolate to future time when the world might be non-stationary, and empirically it seems to work, but there was no.
What I meant to say is I like the historical overview that people have cared about
Oh.
these kinds of problems.
Oh, for sure. Yeah. And then more generally, I mean, he mentioned, hierarchical Bayes. I mean, assuming that the data comes from one distribution is like a very limiting and naive assumption. And many fields outside of this workshop have already thought about that and have lots to say. Hopefully we can learn from them.
I definitely agree with that. I also liked, by the way, the Rich Kuran's historical overview of kind of multitask approaches. And to me, actually, the more you think about that, the holy grail of initially statistics and then machine learning was generalization. But in what sense you understand generalization? I mean, we're just trying to go one step more general in terms of defining generalization. Yeah, idea assumption and generalization there was like data coming from same distribution. Well, define same versus different. Yeah. So what does it mean to go out of distribution? But I'm trying to say that multitask, continual, which is like just multitask in time, meta, out of distribution generalization, finding like invariant causal representations like IRM methods and so on. Everybody is trying, and more recently, scaling and few shot learning due to scale is essentially, to me, all different attempts to solve the generalization problem in machine learning at more general level, where out of distribution is essentially just like a distribution shift, and basically instead of shift from training data to test data. So it's just like we're going in the same direction, just further. So yeah, it is very timely, and yes, it would be great if it became like a part of mainstream, because I think IAD is so yesterday.
Thank you. So maybe follow up on what Irina was saying. So when we're typically thinking about transfer, meta learning, and so forth, even continual learning, we're talking about like distributional shifts, or we're talking about things like this. So the question is, when we're working at scale, to what extent can we still, like, to what extent can we measure this distributional shift? So a particular example, you mentioned few shot learning of really large scale models. To what extent do we know that those systems are actually doing few shot learning? To what extent do we know that those test points that we're looking at, they're different from the training set and they're not actually part of the training set, and it just the training set has become so opaque because of scale that we don't know whether that's the case. So this was a question from Slack that I've kind of rephrased a bit, but yeah, I'm not sure if anyone has an answer.
Yeah, I don't know much about scaling, even though I'm at Google. I have lots of colleagues who are experts on that. I actually think from a scientific or academic point of view, I know there's a question about what can academia do. I think lots, right? I think basically scaling just obfuscates the fundamental scientific problems. I don't know if Shai Ben David's in the audience, but like some foundational work about what's possible and what's impossible, those results don't stop holding just because you have a larger model. It just becomes harder to find. Maybe you get bitten later, but you're going to get bitten eventually, right? You can't pre-train on all possible data sets. There's going to be things that are novel, but like if you're training on the whole internet and you test on stuff that's uploaded to the internet, the chances are that it's like some combination, it's like literally some meme combination of what you've already seen before, and you're going to do pretty well. Something radically novel comes along and the pre-trained models will help you be robust. It's better than having no prior knowledge, but eventually, you can always concoct a distribution that's arbitrarily different from what you've seen. And then the question is like, how quickly can you adapt to it, right? And humans are very, very good at this. And our machines are still not good at this, right? Someone was tweeting this morning about, self-driving cars, like still need, right, ridiculous amounts of human engineering, and they're very data hungry, and they're very brittle, and they fail in very simple tweaks to the environment where the lighting changes or there's like a tree in front of some vehicle. And so, for text data and web stuff, we're in great shape because we brute forced our way through it. But in physical grounded environments and biological data sets and, the weather and so on, we have better tools. We're making progress, but it's not solved. And, I don't think we can just brute force our way through it by scaling. Scaling is not all you need. You can tweet me on that.
Okay, and I'm gonna argue with that. Okay, so first of all, the question was, well, how do we know that the tasks, the downstream tasks, are not just buried somewhere in training data? And okay, so there are definitely multiple studies where indeed the effort was made to make sure that that's not the case. Again, I cannot immediately point to specific things right now, but for example, with transferring knowledge to new programming languages. Okay, so you can say that, yeah, Copilot and Codex, they could have been just taking pieces of code from what they were trained on and recombining that. But when the model kind of starts learning new programming language, that seems to be a bit further from what it's seen. Again, so my general feeling is that the model have those models, well, starting from GPT-3, famous paper that is a few short learner, they've been tested in tasks that they were definitely not directly trained on. Well, obviously because they were trained in unsupervised way. So it doesn't seem that it's simply memorization and just kind of getting the results for the new task because they were some memorized somewhere during pre-training. It seems to be true generalization happening. CLIP, for example, zero-shot generalization, basically out of distribution generalization to very different type of images, well, what you would really call out of distribution, while whatever state-of-art model they compared with, it was like, well, trained on ImageNet. I mean, like few percent accuracy out of distribution generalization, and CLIP is like, I don't know, 70, 80. So to me, something interesting is actually going on with scaling. People talk a lot about emergent properties and so on and so forth. There could be different like theories about that. There is lots of recent interesting studies on, well, quote unquote, phase transitions in scaling. But I don't think that their capacity to solve new tasks are simply because they remembered something like that during training. I think it's way, way beyond that. Sure. Yeah.
Just for you, Irina, regarding to this, I mean, you talked about memorization, but what about interpolation versus extrapolation? Are the system just interpolating? And is that all we care? Because the question is, if it's about interpolation, you know, obviously it will not always scale to everything. You'd want them to extrapolate.
Unless, okay, yeah, it is a good question. Yeah, so like we just
sit next to each other. You're going to be rolling the show.
we were just having discussion with Kevin over the break, and I was mentioning it before for a while in different slides that assume the world is such that it's, well, in some sense, representable in finite basis. It may be a very large basis, quote unquote, and I'm not saying it's like an, well, simpler example would be you have like linear space and you're just learning autoencoder like SVD, and you just like in continual learning setting, just sampling data from different subspaces one after another, and you learn components. But if your world is such that there exists finite basis in which you can represent everything with sufficient accuracy, once you have sufficiently many diverse data sets and sufficiently large model to represent that knowledge, you kind of grok it. And as I was joking with Karen, well, that's where AGI emerges. Okay, side joke. But basically after that, you can probably do much better on downstream tasks. Or maybe the world is not representable well in any finite basis, I don't know. But it still seems to be okay. So that's what you would call interpolation. So finding the components and recombining them in a way, like, I don't know, but talking about compositionality and recombination, then is that interpolation? Or is it what we also do? We like learn the basic components of knowledge, and by recombining them, we're able to solve different problems. To me, that's what the system seems to be doing. But again, it's a bit of a hand wavy argument because we're not talking formally right now.
Yeah, maybe I can add to that, because I feel like scaling up, yes, is very intriguing, and it's the way forward, and it seems to be, these models seem to work so well. At the same time, there was a question about like the role of academics, and if we scale up like this, indeed, in the end, we don't know anymore what we're really like. We don't know what the data is that we are training on, and we know very little about what's actually going on. And in that sense, I feel like um, there's a role for academia to also, maybe not at that big scale, but at a scale where you can still get hold of things, try to get some of the basic fundamentals and better understanding of what's going on. Because we're building stuff, and as well, it's only the big companies that can actually run these very big models. And then we run things, but we don't know, and we cannot compare because they are not trained on the same data. And it seems like very empirical and not very like the science or the theory behind it seems to be lagging behind. And then indeed you can come up with conjectures, like it might be some basis that we're learning, but it's very difficult to prove things. And so that's where I think that there's also room for doing stuff at a smaller scale where we still can control and we know what is the data that we're working on. Or we might even have synthetic data where we know exactly what's there. And if you work with synthetic data, you can also have a huge amount of data, but at least you know this is the data, this is the variations that we allow, apply to the data. And you can have some theory behind it. And I feel that's sometimes lacking with the very large scale stuff.
Yeah, just very quick comment, because I want to give. So I think the analogy it becomes closer to natural sciences, because even with physics you can have simulations of very small, like 2 or 3 body kind of problems, and you can simulate and understand, and then you have natural system and have statistical mechanics. So I think we're at the point of statistical mechanics of machine learning, and then you start treating it as empirical science. And recent scaling laws of, originally power laws of Jared Kaplan and collaborators, more recently, exponential from Surya Ganguly, and more will be coming. It really becomes like empirical physics, where you try to do experimental analysis and see if you can discover any relatively common laws of behavior, because at this point your theory changes its level. You're trying to have statistical mechanics and thermodynamics. You're trying to define what is the temperature, quote unquote, and pressure of that networked system, roughly. It still can be science, but it's somewhat different.
So I think, it's appealing to think that you can just scale things up and everything's going to get better. And it is exciting to have models that are, approaching brain scale. So I find that part exciting. I really don't believe that's the answer. And the reason I don't believe that's the answer is that clearly these models ingest way too much data in order to get to good performance. And we've seen in biology, not just with people, but with animals and birds and so on, they learn from a lot less data. Yes, there is a prior structure, so maybe that's part of the answer, but I also feel that we just don't currently have the right algorithms in order to do really rapid generalization. And one aspect I think is extrapolation. Another aspect that I just wanted to bring up is planning. So in terms of, how do you compose knowledge and how do you put things together? One of the things that is quite salient is sort of looking forward, not just interpolating between tasks, but actually planning to achieve goals, right? So that's partly what reinforcement learning is about. That's partly what biological systems do. And it's not clear to me that the current large-scale systems do that internally, or that they're particularly adequate for doing that. And I think there's actually quite an interesting, perhaps, research agenda to be had there in terms of how do we use these kinds of systems for planning. In terms of what academics can do, I think I agree that part of it is going to be an empirical science for these large models. I think part of it really is to try and understand theoretically, and there isn't really in my mind a conflict between these two things. And there's different places to do this kind of stuff, right? So and to my mind always the analogy that comes is between chemistry and chemical engineering. Like chemistry is really necessary in order to discover the basic reactions, and then chemical engineers take these things and build plants and make sure they're stable and run them at scale and so on. And so in some sense, the distinction of what's happening in academia now and what's happening perhaps on the industry side and these large scale models is maybe that we're starting to go in that direction, where maybe in academia we really want to find the fundamental principles, or in basic research we want to find the fundamental principles. And there is also a side to it of, then how do you actually scale, deploy, make sure that these things are robust, and all that. And that is, perhaps going to be an empirical and engineering driven endeavor.
Sorry, can I just jump in? I like the chemistry chemical engineering analogy, but chemical engineering is also taught in universities, and there is a scientific basis to it. I actually don't really know much about it, but it's just not ad hoc hacking. I mean, otherwise we'd all be dead because of poison, and our power plants would blow up, right? Whereas like computer science is total ad hoc hacking, right? It's like kind of shocking. I mean, computer scientists are just not held to the standards that other engineers are, and it's really a scandal for society, frankly. So.
Just a few things. Very quick comment about the classical argument that babies do not learn from million samples and they just need a few. Well, they're few short learners. They're pre-trained large-scale systems, and the evolution was a pre-training process. So it's one way to look at that. So we're kind of getting the large model, well, babies starting to do their few short learning as well to an extent. I'm not saying that we completely solved babies, but the second question is, what can we do with academia? It kind of implied that we don't have large compute. Well, I wouldn't be so pessimistic, because there is lots of resources such as supercomputers. I'm doing a little bit of advertisement there, so just people are aware that scientists in physics and biology and chemistry, meteorology, and so on, for years they were actually aware of and applying for and using large compute in supercomputers, whether like Summit and now Frontiers in the US, Jewels in Jülich Center in Germany. Big Science just trained the large-scale 176 billion model on Janzé in France. Sweden has their own. Anyway, so every country has at least a few supercomputers, and this will be continuing because they're all, of course, competing in terms of who has better supercomputers. And scientists, including AI scientists, are welcome to apply for that compute. So, for example, we did apply, we got some intermediate, we'll see what happens with large one. There are companies out there who are starting to provide compute to non kind of, well, basically open source code and open source data sets. So it's not necessarily that academia is kind of doomed in terms of compute. There are possibilities, and I just encourage people to explore it. So it's not just we're going to be analyzing and deriving scaling laws and or just doing the science of prompt engineering on top of existing large-scale models. We might get a chance at training them. Having said that, actually there is a lot of interesting things you can do on top of them. Just like Hugo was talking yesterday, there is a knowledge acquisition part, training, and there is knowledge mobilization, well, prompt engineering and so on. And there is lots of, it's totally unexplored. They become more like natural systems. You don't quite know how they're going to behave, under what conditions. And there is this emerging field of, well, AI safety, AI alignment, which, well, different people understand in different ways, but essentially it's about how do you make sure that this very complex system now behaves in ways you would like to and doesn't behave in ways you don't want to, whether it's robust to distributional changes, interpretable, whether it's going to get into reward hacking mode or not. So there is lots of research on this. Well, you can call it AI alignment or studying behaviors of those systems. And this is totally wide open and I think very exciting.
Thank you. Actually, I'll add a few things on that as well, because it seems the conversation is quite active. So I wanted to say that also, like, I think maybe an issue in this question about like how do we interpret the results of large scale is the metric itself, performance. Maybe performance is not that well, like accuracy is not that well defined when you're at this scale, because it's harder to understand the relationship between test data, training data. So I'm actually wondering if people in the panel agree with me, but I'm thinking that maybe continual learning, meta learning, and all of these things may actually offer a solution for a different way to to evaluate the systems. And in particular, like I'm interested of your opinion on looking at the speed of learning or the speed of acquiring knowledge as the metric that we care about. So rather than caring how well the system does zero-shot generalization, which I think it's very ill-defined because we don't know exactly to what are we generalizing. The question is, can we look at how quickly the system can continually learn and say we have a good architecture, we have a good learning algorithm. If this learning algorithm is able to incorporate new information efficiently, which I think is sort of what biological systems tend to do. I don't know if anyone has a thought on this or if this would resolve the problem at all. Yeah.
I could, but okay. So again, just was discussing with Kevin in the break, was showing that I clear this year paper from Google, Ethan Dyer and co-authors about basically exploring catastrophic forgetting at scale. So I mean, it's just one example. There are other works showing that, okay, as you scale amount of data, but to be honest, you need to scale the diversity of the data, as everybody's saying. You need to scale amount of information pre-training data. But as you scale that and you scale the model size to the capacity that is sufficient to incorporate that information, it looks like the trade-off between forgetting and adaptation gets better. At least, well, results in that paper show that if you have, say, up to 10 tasks, subsets of say 100, catastrophic forgetting disappears when the model is sufficiently large. It's promising. They didn't never say that scaling solves catastrophic forgetting, but they show that it definitely improves continual learning on top of such systems. This morning we had a talk by Alexei talking about how representations of large-scale models can be better for subsequent learning. In the Google paper, they continue fine-tuning, but definitely like starting from the pre-trained model and then doing continual learning may be much more efficient. And yes, you can probably measure the quality of the pre-trained system by how well it's going to solve the stability plasticity dilemma later on. Yeah, so you don't want to train it in a way that it's too rigid because you still want it to be able to adapt. But yeah, so I agree it could be, continual learning could be a good test for the quality of large-scale pre-trained models. But there is evidence that they seem to be improving continual learning as compared to training from scratch. So that's good.
So I just want to add one thing. Like, to me, always machine learning is about future performance. Like, whether it's continual learning or usual learning, you want to get a system that is as good as possible in the future. And so in some sense, in continual learning, this is very natural because there's going to be distribution shift. And so you want a system that somehow makes that trade-off well. So I know that there's been a lot of focus on catastrophic forgetting, but maybe forgetting is not so bad, right? Because what you really want is the system to do well in the future. If you're forgetting something that is irrelevant for the future, then that's perfectly fine, right? It's not a big deal. So, now exactly formally defining what that means, I think is a really interesting question, which is different in reinforcement learning than it is in supervised learning. Yeah.
Maybe I can add one short comment here. I think I agree that it's important also to have multiple metrics, and metrics themselves are really important because as academia, or well, like not just in academia, but all of us, there's this tendency to really optimize for the metrics, and it's the metric you define that determines what people will focus on, because if to get your paper accepted, you have to outperform the state of the art, so you have to beat the others in terms of that metric that has been defined. And so by focusing too much on one particular metric, there might be a tendency to focus maybe on the wrong things. So having a multitude of metrics, including like the one you suggested, and probably even more, is something that I welcome very much, because that will create more diversity in the field, and yeah, avoid this overfitting to one particular aspect.
Yeah, I want to second what Doina was saying. I mean, if you focus on future performance, you just have to make your assumptions clear about the data generating process, right? what is constant, what is stationary, which parts are changing. And then given those assumptions, you can, in principle, you can write the Bayes optimal thing, but it's intractable. And you just want to be as close to Bayes as you can within some compute budget. And then you have to justify that your modeling assumptions are reasonable by checking model fit and out of distribution generalization. And that's it, right? It's actually fairly clear. You just need to write down explicitly, okay, I'm assuming that this task A might occur in the future, because what does that mean? It means that you assume the distribution is some mixture of distributions where you can cycle back. You could think of it as like an HMM, right? And you actually might revisit the past, and therefore you should remember the past. If you can never go back to the past, then it doesn't matter. You can forget it, right? And are you going to suddenly shift, or are you going to slowly shift? Well, then the model that you need to use depends on those assumptions, right? If you don't know which, then you have a flexible model that's non-parametric, and it can do one or the other, right? And you just want to, they're computationally difficult, so then it becomes an algorithm problem, but at least statistically it's well defined. And in which model class? Well, you just do model checking, right? You see how well does it fit the empirical data. And I think, if we go beyond, one thing Rich Caruana said this morning, which I really like, is like the field is just so obsessed with like squeezing high dimensional signals into 1 of 10 labels. I mean, there's much more to the world than just a few labels. So he was pointing out that let's try to predict many things simultaneously, right? Like the pressure and the temperature and the wind speed and whatever at many locations. So it's a multi-dimensional output task. And in the limit, that's what generative modeling is, right? Predict all the pixels, predict all the words, predict everything that's going to happen next, right? And if it's conditioned on the past, then, these discriminative models and generative models are basically the same, but it constrains the problem much more, and it's much more interesting. And then you can't talk about, I mean, you could talk about accuracy, but like along which dimension? Maybe you're great at predicting temperature, but not at pressure, or you're great in North America, but not in Asia, or whatever, right? So it becomes much more nuanced. It's a multi-dimensional vector, and then what you focus on depends on the task, right? So it might be that you actually are launching a system in Canada, and you don't care about predicting weather in Asia, right? Or vice versa. So you just define your goals clearly, and then show that you do as well as you can, subject to those definitional constraints. And someone might object to your assumptions, but that's sort of a separate issue.
So I'm going to continue with the question from Ryland, who just posted on Slack, and I'm going to change it a little bit. But his question is follow up on what Doina said about animal learning quickly. The amount of information in a genome isn't enough to encode neural network explicitly, suggesting that the genome instead encodes some systems capable to bootstrapping itself to reasonably high level of performance. And the question is whether there's been research done on this. And just to augment a bit the question, I think in RL specifically, Rich Sutton has been pushing this phrase if the world is much bigger than the model, which is sort of like an underlying assumption of why continual learning is needed, because the world is so big and the agent can't represent it. Yeah, I'm wondering, how do we reconcile this with what we're doing in deep learning, where we always in this overparameterized regime, and we're always in a place where the model is actually much larger than the data most of the time. Like, is there a contradiction? Is like sort of CL the place where we'll end up exploring this alternative when the agent is smaller than the world?
If nobody wants it, I'll pick up on that. I mean, I am very much of this opinion that the agent is smaller than the world. That's almost a tautology, right? Because the agent is part of the world, and so clearly, the world includes the agent and many other agents, right? And so, we need to make sure that the agent can adapt and adapt quickly, and this is where continual learning comes in. I think there's a really interesting question of, the sort of expanding a system, like taking a genome and expanding out of that a brain and all of that. And perhaps one of the ways to think about that, at least from an RL point of view, is whether you want policies that are, a network that maps, observations to actions, or whether you want to have programs, right? And program can, do many other things, including, construct stuff. And I think there are some people in the research community who are looking at that kind of question. It's a really interesting question. If you're doing hierarchical reinforcement learning, it's very easy to think about that, because you can have these sub policies and they can be programs, and they can have memory in principle. So that's a very flexible representation. We don't know how to deal with it very well, I think, to its full capacity yet.
So you can have policies and programs. So policies are just, it's just amortized inference, right? It's just faster because it's too slow to run your program. So your program's your inductive bias, you have some structural assumptions, and then like you distill it into a neural network that's feed forward and fast and maybe is actually more accurate because it like can soak up from the data what you couldn't model explicitly. But it's super statistically inefficient to be groveling around in the parameter space of a billion parameter model. You should be up there in your hierarchical space with abstractions and objects and stuff, even though it doesn't fit the data perfectly. And that's like, it's like high level model search. And then it tells you sort of where to focus. And then you fill in the details with data. So with a flexible black box model. So I think we need hybrid models.
Comment. Well, don't you think that perhaps in these large scale models, you might be already constructing those high level representations implicitly, higher level? An example is, say, if you can pre-train a model on language, and just by adding a few adapters here and there, you can switch it to images and it does a good job. Doesn't it imply that it might have learned high level representations and concepts that are common between language and images? Or if you can train language models and then just apply to sequential decision making, like decision transformers, and it starts acting. It doesn't mean, it doesn't prove it, but it's plausible that this transfer is happening. Transfer between very different domains might be happening because it already is starting to kind of learn concepts, high-level concepts, but not explicitly within that like large-scale humongous network. So because just like the range of the transfer that seem to be happening with large-scale models is kind of scary.
Maybe one other comment, like based on what you said, it's interesting to see that when we say we scale up typically in 2 dimensions. On the one hand, we scale up the data, but simultaneously, we also scale up the models themselves. And it seems that so far, these two go hand in hand. It's not just the same model and we scale up the data or just bigger models. It's to get better performance, typically we need bigger models for larger amounts of data. But then if you say indeed like, well, ultimately, there's more data than can fit in a model, I wonder whether indeed, yeah, we cannot keep scaling up the models. If we say we want to learn more, we want to really go to continual learning, some infinite data, we cannot have an infinite model. So yeah, I think at some point we will come to a limit there, and we kind of avoid that at the moment by just making also the models bigger and bigger. So yeah, it's not a solution, but I think it's interesting to see what that would give.
Thank you. So I liked a lot what Kevin said about the programs and policies, and I want a bit of a follow-up on that. So I think a lot of times we get these big models and we're trying to fit things, and even for example for the weather simulations that we're talking today, we know that some of the underlying physics that is needed to do those simulations require a particular amount of compute, something like n cube or whatever, and we're going to end up doing this with like O1 amount of computation because the model is fixed and the inference is always fixed. Is that a problem? Have any of you thought about like how can we move from this kind of systems that perform a fixed amount of compute for regardless of what they're trying to do? Is that sort of a sign that this kind of line of research will need to get stuck because we're not allowing arbitrary amount of computation in order to do different kinds of predictions?
I mean, if you think about Bayesian inference, a lot of algorithms are iterative, right? And optimization too. So you could do that on the fly, and then often the mixing time of these things depends on posterior uncertainty, and so you will actually converge quicker if the problem's easier, right? It's more similar to something you know. And if you distill that into a finite length circuit, there's work on, I think you've done work in computer vision where you can like jump out of the network early because it's like a pretty obviously a cat. You don't need to go through 100 layers. So like things like ResNet and whatever are basically just circuits that are unrolled. And I think, these works on neural differential model, neural equation models and so on are explicitly iterative, and you can control the compute time. and you can have some compute accuracy trade-off. So I think we already, I mean, we don't have the final answer, but people are looking into that. I think it's a great area.
Just quick comment. Yeah, I mean, indeed, back to what you said, indeed, to achieve best performance, you have to simultaneously increase amount, well, and diversity of data and the model size and the amount of compute. So, for example, the scaling laws were indeed shown for the all three variables changed simultaneously. And essentially you allow one to grow while you do not constrain the other two. Like what's the best you can get for this amount of data if you allow whatever compute you need. I'm just talking about the famous 3 pictures from Jared's paper. But yeah, so you have to do those actually 3 things simultaneously to achieve best performance. So yeah, just a comment.
Based on a question asked from Slack, so we've been taking into account this assumption that scale actually is going to, like, due to scale, some interesting things are going to emerge. The question is, do we need to rethink how we parallelize in order to achieve scale in settings like continual learning? Do we need to rethink parallelization? So continual learning by definition wants to be a sequential process where you need to learn one thing after the other. But the question, if we are doing that, then we're not going to be able to properly scale. In particular, I think the question is referring a lot about RL and saying like, okay, if we're doing RL, like, can we actually have multiple actors interacting with the environment and mixing this information? Is that a fair thing to do? It feels wrong. It feels like there's only one agent interacting with the world, and then we can't scale anymore because the amount of experience is going to be quite limited.
So I very much like the single agent perspective, and I think multi-actor systems are really a crutch that we've come up with because we wanted to solve the exploration problem. One way to solve the exploration problem is just to start multiple actors in different part of the environment, and that way you make sure that you have enough diversity of data. Otherwise, in RL, because the agent generates its own data, we can really get stuck in some uninteresting part of the world. So I think to me at least, RL should be single actor. There's no problem with that. Now the question is, how do you then find enough interesting things to do? And I think the answer really lies in predicting many things and trying to also learn how to do many things. And you can do that from a single stream of data, right? This is in some sense what general value functions and off policy learning are about, right? So the agent can think about predicting many different variables that are in its observation and many different timescales, doing that all at the same time. The agent can think about, and imagine trying to control different parts of its observation, for example, or trying to control different parts of its latent space. And it can do planning. It can do planning in its head. So if the agent has a generative model in its head, it doesn't have to be multiple streams of real data. It can be just synthetic data that the agent is imagining and projecting forward and using to learn. So to me, that is really the answer in the case of RL agents, is to have synthetic data that the agent generates for itself and tries to learn from, and to just look at many different parts of the observation.
Well, I'm not. I don't know much about RL, but I guess apart from, and so I guess you have a point in that context. But if you look more generally, and we look at biological systems, then language plays an important role, and language is communicating between multiple systems. And without language, the level of intelligence arguably would be much lower. And without interaction between different agents, the learning process would be much slower. So in that sense, it makes sense to have like multiple agents. And indeed, just for sake of compute, if you can parallelize things, that would speed up than if you really do it sequentially. And there's like federated learning and stuff like that. So I think maybe not in an RL context, but if it's just about making sense of images and language and stuff like that, I don't see why not exploit parallelism and have like things develop independently and then merge them as a kind of ensemble and whatever. So I think there definitely I see opportunities.
Yeah, actually, Yeah, some adaptive continual learning. I really agree with that point. I might be a bit biased because I just like multi-agent RL, and I have this generic belief that, I mean, intelligence never developed in isolation. There was never a single agent. There was always a population of cells, population of animals, monkeys, humans, but intelligence may be developed in order to be able to survive as a part of that population. We can, of course, say that artificial intelligence doesn't necessarily have to follow anything that evolution did. Fair point. But at least I think that you can really speed up learning, as you said, if you consider populations or groups of agents. And another thing is, in terms of non-stationarity, we're in continual learning kind of conference here. So non-stationarity in RL often comes, like people say, not just from changes in the environment. Environment can be static, but because of other agents, that's kind of source of non-stationarity. And then the whole notion of like the need of having the theory of mind to represent those agents. So I think this multi-agency would be at least efficient way of developing intelligence faster. Instead, in terms of being more distributed in terms of learning, yeah, I think it definitely would be interesting to explore. And large scale can be distributed in space, federated learning, or in time, continual learning. So I would say that it would be a very interesting direction of research indeed. That's basically just.
I just want to quickly clarify that I totally agree that multi-agent RL is very cool, and having multiple agents can be really good source of non-stationarity. But there's a distinction between multi-agent RL, where you have multiple agents acting in the environment, and multi-actor, where really you have just one agent, you just happen to clone it and sort of put it in different parts of the environment, and you just take all the data together and do the learning. So really there's just one brain. It's multiple streams of experience that come together. And so that's the thing that I was more talking about. But multi-agent RL. That was the early success. The next success is going to come from single agent. Don't quote me on that. But that's my hope.
So another question from Slack. So what is your opinion, what is in your opinion a meaningful way of partitioning neural networks according to their functional components? Example, usually in supervised learning, we partition the learner conceptually into a feature extractor and then a classifier. Maybe it makes sense to think about the partition as a feature extractor, world model, task solver, maybe in an RL sense. There is even a pointer to a blog from Jan LeCun that I'm not sure I read. Which part of this conceptual which of these parts are conceptually easier to pre-train using a large scale learning? All of them, maybe none of them. Is large scale meant to just learn certain components?
Well, what I can say, I mean, it might be interesting to focus on like clear compositionality and kind of study those components, but I don't know if it's necessary to actually achieve a good generalist agents, because you can, well, scale transformers, use attention mechanism without specifying very clearly that, well, this part is responsible for A, this is responsible for B. And apparently, well, Gato, you seem to be able to train something that can solve quite a wide variety of problems. It remains to be seen how Gato can be learning continually after that, and I guess probably people working on that. My point is, while explicit compositionality and engineering of components comes to mind, definitely it's one way to go, I'm not completely convinced it's necessary. Those things may emerge actually.
Maybe I can follow up on that. I mean, if we do end-to-end learning, we know we're going to have all this issue with continual learning and all sorts. I mean, most of these problems come from like global updates to all of the parameters. Wouldn't a decomposition of the model help. In particular, the other thing that I will want to hear an opinion, like lately we've been focusing a lot of neural networks, but if you able to do this decomposition, maybe some of the components can become like non-parametric, Bayesian approaches that we know do not suffer from catastrophic forgetting. They do not suffer from a lot of things, and somehow they're not really used nowadays as much. I think, at least from my experience, wouldn't like thinking about this decomposition open the door of incorporating back these tools that have lots of advantages that neural nets do not.
Yeah, so I mean, you can have the best of both worlds, right? I mean, so maybe what you're getting at is somebody asked earlier about latent feature models. So I'm a big fan of those, and they can be nonlinear, and then that's like, it's like one half of a VAE. And so, which parts are I mean, some of these parts are going to change, and some are going to be invariant. So I think with self-supervised learning, it's basically, it is a feature extractor, but it's not. It's designed to reconstruct the input, or like, predict masked patches or whatever, as opposed to being class specific. So a lot of the stuff we saw earlier this morning on pre-training, relies on JFT and its billion labels, but labels don't really matter. It's just some notion of similarity that these two things are closer than those two things, and that's now, I think, well demonstrated. So yeah, I think with that that's like a new basis for your data. And now you could imagine pre-processing all your data through that lens, and now building generative models on the features of these models. And then that, opens up new games to play, I think.
Basically, this question also made me think about, well, similar kind of discussions and ideas in continual learning. But think about that. You can either start designing parts and combining them explicitly, engineer them, or you can let something like regularization-based approaches, AWC, on decide which part's going to be responsible for what. So essentially, it's the same question, like, do you want to engineer things manually, or you want to create kind of settings in which they will emerge, and maybe something like regularization-based approaches can lead to changes in some weights more than another. And effectively, you will see parts of the network emerge which have this functional specialization. And I can admit that I'm always biased towards more hands-off approaches, and eventually trying to automate and keep automating as much as possible, and instead of like manually inserting, well, inductive biases. I mean, it's like, don't take me wrong, I'm like not enemy of inductive biases completely, but I just don't want to overdo them. So essentially, in this sense, maybe if you have flexible method that lets the system decide which weights and which parts are better be changed and specialized, like, again, by analogy with evolution, when the brain was evolving into functional components, unless you believe in God, nobody engineered them this way, right? So some kind of EWC let you develop things properly. I know, perhaps.
Okay, I think we're out of time. So let's thank the panel. Well, part of them were there, but yeah, if there's, yeah, we could take one question. I mean, if there's, oh, okay, you maybe, yeah, maybe we could take one question.
Good. Yeah, cool. Thank you. So my question is about, you said we should model the shift in the right way, but how would you consider a right shift? For example, would Markov chains be a good model for continual learning, so that, I mean, it's better than class incremental, right? Like, how do we actually define continual learning in a useful way that can model, for example, RL problems, or in applications that we actually need? Because you mentioned that if you never revisit a task, we better forget it. So catastrophic forgetting to me seems to be inevitable if you define the RL, if you define continual learning as such. But do you see other alternative models of the data generating process that can give better results? Yeah, but like, how would we define the shift? Like, we need to define, right. Uh, right. Oh, really?
Okay, so yeah, I totally understand your frustration with how we define the scenario of continual learning. We had talks this morning, right? I mean, many people struggle because it's like a bit of a continual learning is a wild west. Everybody like comes up with their setting, and then people trying to classify and characterize those settings, and there is some classification so far, but there are probably never going to be like single type of shift. So you may have the main shift, you may have the, well, basically you have like several variables and you can define them like what exactly changes, like conditional distribution of class given label, or maybe there is no class even. So there will be different types of shift and different settings. So probably there are always going to be a family of continual learning settings. And for your application, you will either find the appropriate one or define your own. And that's okay, as long as you are clear about assumptions, what changes in your domain. But I don't think it's realistic or even needed to have a single definition of shift and continual learning. It's more of a umbrella kind of topic, right?
Yeah, one pragmatic approach might be look at where current models fail and try to build data generative processes of the data on which they fail, and see if you can find out which aspects of that model are changing, so that, you know, it was trained on one, the model, the distribution shifted, it fails horribly. What part of that data changed that caused that failure, right? And just repeat that exercise for a set of data sets and see if you can find out general patterns of like, okay, if I fit it with a VAE, is it just like the decoding network changes in one layer, or is it like the prior, or is it like it's a low rank shift or whatever, right? And there's going to be many kinds of shifts, but like ideally there's some common patterns, and then you can tackle the common pattern, right? Or maybe it's not common, maybe it's like a rare species, but it's a big deal because like it's like medical imaging problem, whatever, right? That is not typical. You don't see it on the web, but it actually matters because people's lives are on the line, right? So, you know, you have to just pick something and then see if you can formalize it, and then once you've distilled it into a model, then you try to solve that model, right? And hopefully then if your assumptions are reasonable, then once you've solved the model, you also solve the problem.
Yeah, I guess it was more or less in line with what I was going to say. Like, basically, to me, it seems like there's two steps that probably we need to tackle. On the one hand, we can say, okay, given this model, do we have ways to solve things in a continual learning manner? And then we can use synthetic data that entirely fits that model. And then if we have a whole range, like a whole zoo of different models, it can be Markovian or whatever, where we say, okay, for that model, we know how to solve it. That model, we know how to solve it. And then there's a next step, and that's like then going to real world data and then see, okay, which model fits our real world data, and then see whether we can generalize to that setting. But I think we need to have, yeah, it's good to do it in two steps rather than trying it all at once.
I'm then just gonna plus one, it's okay to have different kinds of shift models, and they may be slightly different in RL than they are in supervised learning, and that's fine too. And some people will use the real world, real data to inform that, and some people will use theory, right? They'll look at the shifts that where you can prove something, like there's going to be a sample complexity result or some other interesting theoretical result. But yeah, there's not going to be one answer, and there's going to be also some negative answers, right? Like that if things change arbitrarily, for example, then there's nothing, you can't do anything, right? It's hopeless. So, and that's okay too. There will be plenty of interesting problems where we can still prove or show empirically interesting results.
Thank you so much. Let's thank the panelists. So